Hello and welcome to Beginner's Code with another new video. Today we are going to review paper which is a very classical computer vision paper named as Rich Feature Hierarchies for Accurate Object Detection and Semantic Segmentation. So basically it's known as RPNN, Regional Proportional Convolution Neural Network. It's a series of paper. Today we're going to discuss this paper, but later on we're going to cover all of other three papers, which is known as fast RCNN, faster RCNN, and then mask RCNN. But today we're going to cover only this paper. This paper is written by Ross Krishke, and these are the other authors, based on the Berkeley University. And we're going to see about what is written in this paper by each and everything, and we're going to review, we're going to understand what was the key objective, what was the methodology of this paper, how this paper actually, how the algorithm of this paper actually works, and we're going to look each and every aspect of the paper. So try to focus on listening. We're going to display a lot of things and just trying to be focused, and you will get to know it's a very classical paper. So let's start with the abstract. In this paper we propose a simple scalable detection algorithm that improves mean average precision map by more than 30% relative to the previous best results on VOC 2012. This is a data set achieving a map which is mean average precision 35%. Our approach combined two key insights. So here they are telling about the approaches. One is that one can apply high capacity convolutional neural networks to bottom up vision proposal in order to localize segment objects. So this part is saying that they're proposing a method which propose a regional areas. We're going to look on that later. And when label training data is scarce, meaning that when label data is inefficient, is in low in quantity, supervised pre-training of an auxiliary task followed by domain-specific fine-tuning yields a significant performance boost. Since we combine the regional proposals in the future, we propose a method RCNN. Before that, they say that object performance measured on the conical Parker dataset has plateaued in the last few years. The results were not improving. Over here, they said that before it used the shift and hog features. These are the two features which used for the extra low-level features. And over here, this part from here to here, they tells about the history. This section they tells about the history of the paper and history of the convolution neural network, not convolution neural network. That how the approach is developed over the time. And then over here they display the all the approach of their things. So this diagram they display there, and now we're going to look with all of these in the terms of slides. I found these slides online, so I thought it would be nice to show you in form of I will drop a link of these slides as well. Remember I told you about the plateau thing, so that was the plateau, the mean average precisions. In 2007 the precision was about this thing, in 2008 precision was about this thing, 9 over did this percent, 10 and about 7%, but in 11 and 12 it was stable, it was not increasing. And whereas shift and hog and LBM, these are the type which extract the low features of the image. These are the methods basically. The RCNN improve way better in these, in as you know, the post-computation results. As you can see that RC performed 58.5% RCNN on these all that data set, and on 2012 it performed about 53.3%, which is very good. So this there is the history of the convolutional neural network. The Fukushima Nigoting it's a biological pattern. This is person biological pattern developed algorithm. In 1986, he developed images which developed convolutional network which identify the digits, digits about 1898, and over here this is basically LeNet. This thing is basically basically LeNet, and this is the ImageNet classification, which use convolutional neural network, which just emphasize the user convolutional neural network. So CNN for the bad detection, these are the things till that was open, and the latest thing was by this Pascal detection by the Erhan 2003, they proposed a new network. Okay, so here I'm going to talk to you about some RCNN region with features. So it has basically four things: input image, extract the region. They extract the almost about 2000 images of the image. These are the proposal images, proposal portions. Compress this, compute within, wrap that in the bounding box, compute with convolutional neural networks, and then classify through a linear SVM. So here the first part, step 1 is going to extract the proposal method. Proposal method is used to for the proposal region. They use a selective search method, and and active area, the CVPR, high quality segmentation. They use these the method what they explained by in this paper. And next step 2 is going to extract that region, dilate the proposal, crop that region, and then crop that image, wrap that into the box. Over here this image is just wrapped into this box, and then it move forward to the compute for the convolutional neural network at the 7th layer feature extraction. And the last there is the linear classifier, which classify about the which is what is either it's a person or it's a horse or something else. Softmax for the multiple classification. And the last, when we detect the bounding box using the bounding box regression method. Bounding box regression method, they use these coordinate system original and predicted. Over here they're referring to some of their results, and these are some of the result false positive, and these are these result of the false positive. You can see that it's a bicycle, but it's not an annotated bicycle. It's a bicycle. It's image within an image. So let's move back to the paper as well. Right, some runtime analysis. Result of such sharing data time spent computing a linear proposal and feature on the GPU is it took about 30-second image on a GPU and 53-second image on a CPU. So amount is all about the classes. I mean, to putting a linear proposal and feature take just only 1.3 seconds CPU. Specifically dot product with feature stream based on environment separation. In practice, all dot products for an image are batched into single matrix product. The feature matrix called 2000 by 4096, and where matrix is 406 into n, number of the features, when number of the classes. The analysis shows the RC can scale how to object classify without using approximate techniques such as hashtag. Even if there were 100,000 classes, the resulting metric prediction takes only 10 seconds on a modern multi-core CPU. It's a very high. It's a very That was very high in terms of calculation. In terms of calculation, efficiency is increased because of the nature of the model, right? So the user do high dimension feature would automate to while you can 34 GB just to store linear portrait compared to just 1.4155 GB to our low dimensional features. They compare the techniques in terms of the memory, in terms because they're saying that their algorithm is optimal at that time. So how to train the supervised pre-training? We treat origin puzzle. So how to train a supervised when we're going to look over there in a bit better of time. So now we're going to look at the supervised pre. So RCN and training step 1, supervised pre-training. Train supervision CNN for the 1000-way image classification task. So basically they are using a pre-trained model and fine-tune the CNN for the detection, transfer, precision learn for the model which was trained on this in this I mean in this classification 1.2 million images. They just take that model, that trained model, and fine-tune that to CNN for detection. Fine-tune that on their own dataset, which has 25K object labels. Got it? Fine-tuning that model which is trained on 1.2 million images, and then fine-tune that model on 25,000 object label. To do that, they use CNN library, Python, and MATLAB. They use best fine-tuning and feature competition. Step 3. Train detection SVM with software classifier from fine-tuning map decreasing from 54% to 51%. Fine-tuning little bit decreasing, this accuracy has been decreased to fine-tuning. Compared with fine-tuning RCNN on different data set, these are the results. So now next part we want to see that what did the network learn. So network, they're going to visualize the fully connected SAML layer, visualize what did that see, because at that time it was very curious at what layer what did the network learn. So the feature extraction, position of the receptive field, visualize the image at active pool 5 a feature. They're visualizing that image which is at that time of that layer. So these are the results, some of these things that at that layer, these are some of the images with this percent of the accuracy. Dramatically better than Pascal map, parsing out from other CNN based method or image data detection speed is manageable, 11-second image I've told you earlier. Scales is vary number of categories from 30 milliseconds to 2000 classes are simple and completely open source. They also do some semantic segmentation, and they use that thing for the semantic segmentation. The accuracy CNN were fully connected with non-fine tuning is 47.9% and 40. Yes, that's it.